Welcome to tutorial 22 in the Practical RF Design tutorial series. My name is Dr. Prakash Sangaran and I am a Keysight certified expert. This is a 4-part tutorial. In tutorial 19, we will cover antenna introduction. In tutorial 20, we will cover antenna selection, design and optimization part 1. In tutorial 21, we will cover antenna optimization part 2. In the last tutorial, tutorial 22, we will cover antenna optimization part 3, antenna EM simulation and results and analysis. Let's continue with tutorial 22. Next, we need to create a brand new schematic to place EM model and optimize it. To place the EM model, just drag the EM model and place it onto the schematic. The EM model is at the symbol. This is the EM model that we have created and these are the parameters that we have defined before. Since I have already built the schematic for optimization, I am not going to repeat the process. Here is the fully done schematic. I will walk you through the steps required to create this schematic so you can easily replicate it at your place. I am sure everyone here knows how to place as parameter controller, goal, optim and also variables. After placing the as parameter simulation controller, we need to insert the start, stop and also step for the simulation. Under the goal, we need to enter the design goals as required. Each band has a separate goal. We set goal to optimize S11 to be less than -10 dB across the frequency band of interest 617 MHz to 960 MHz, 1.7 GHz to 2.2 GHz and 2.3 GHz to 2.69 GHz. When entering the frequency, the unit should be entered together. Since we have 3 different frequency ranges, each frequency range will have separate limit. We need to redefine the parameters again using variables or var in ADS. I have redefined the parameters in the same order for simplicity. The X, Y and Z in the EM model are redefined as A, B and C in var respectively. The number behind is the same between X and A, Y and B and Z and C. The value of X1 and A1 are equal, the value of X2 and A2 are equal and so forth. In the same way, the value of Y1 and B1 are equal, the value of Y2 and B2 are equal and so forth. After that, insert the newly created parameters into the EM model. After modifying a parameter, press enter to move on to the next. This parameter redefinition is done because the optimization can only be done via variable component in ADS. Next, on the variables, we need to enable optimization and set the optimization range for each parameter. Each parameter will be assigned an optimization range with minimum and maximum values. Since we are doing discrete optimization, you need to enter the step value as well. With this, all the steps required for running optimization has been successfully completed. The complete schematic for optimization is shown here. Next, we have to just click the button to run the optimization. The optimization has been successfully started. Optimization takes a very long time since the antenna has many parameters, and when I started the optimization, the antenna return loss was far off from the desired goal. To cut the long optimization short, I will just show the results of optimized antenna. Let's close the optimization cockpit. We will now do the EM simulation to get the optimization results. As you can see, return loss of less than -7.8 dB is achieved across the band of interest 617 MHz to 960 MHz, 1.71 GHz to 2.2 GHz and 2.3 GHz to 2.69 GHz, which is excellent. With this, we can conclude that we are meeting antenna frequency, bandwidth and return loss requirement. Next, we have to check if the antenna is meeting the size requirement. In order to do that, go to the optimization schematic, click on layout and click on generate or update layout. When you click apply, the antenna layout will appear. In order to measure the antenna, right click on the antenna, select component and click on flatten and then click apply and OK. To measure the antenna, go to insert and click on ruler. Now we are measuring the X dimension of the antenna. And now we are measuring the Y dimension of the antenna. With this, it's proven that the antenna is smaller than our maximum antenna dimension. Due to this, we are meeting the antenna dimension or size requirement as well. With this, the step 3 antenna optimization has been successfully completed. We will move on to our step 4, which is EM simulation. We will be using RF Pro to do EM simulation. RF Pro is a new EM simulation software that comes with ADS. We will double check our return loss optimized using EM setup and also simulate far field parameters such as gain, efficiency, radiation pattern using RF Pro. Before doing RF Pro simulation, we have to delete the dimension lines and then place pins. After that, you need to create pods using pod editor. To launch RF Pro, you need to click on Tools, RF Pro and New. Since I have created RF Pro, I will just click Open. I will select the first one and click OK. When RF Pro is launched, you will see a nice 3D view of the antenna. You can rotate the antenna with your mouse click. In the RF Pro, as a first step, pins are dragged to the pods. Since I have already done it, it's a duplication of pod, so I will delete this. After that, go to Options and double click on it. Here you can enter your frequency band of interest similar to the EM setup. In order to simulate far field parameters such as gain, directivity, radiation pattern and efficiency, you need to do EM simulation with far field option enabled. You can do that here. Next, we need to select a simulator for the simulation. Similar to the EM setup, we will select momentum microwave. And mesh density, we set it to 50 cells per wavelength. After that, we can click Done. Finally, click on Run to run the simulation. Since the simulation takes some time, I cut the simulation progress short in this video. The simulation has been completed. Let's click on S parameter to check the results. You can add marker to the S parameter plot. The markers are adjusted for a better view of the S11 plot. The antenna exhibits less than -7.7 dB return loss across the frequency band of interest, which is 617 MHz to 960 MHz, 1.71 GHz to 2.2 GHz, and 2.3 GHz to 2.69 GHz, which indicates the antenna meets the specification we shared in a table before. Let's compare the simulation results between EM setup and RF Pro. This is the EM simulation results of EM setup. And this is the RF Pro EM simulation results. As you can see, excellent correlation is achieved between EM setup and RF Pro. Next, let's look at the far field parameters. Double click on far field. On the results type, we want to monitor the gain. And frequency, we will start from 617 MHz, which is our lowest frequency of interest. The radiation efficiency is 96%, whereas the system efficiency is 80%. You can see the radiation lobe is omnidirectional. The peak gain is 1.66 dB. Let's change to the next frequency, which is 960 MHz. The radiation efficiency is 95%. The system efficiency is 82%. The radiation pattern is almost omnidirectional. The peak gain is 2.08 dB. The next frequency we will be looking at is 1.71 GHz. The radiation pattern is directional and the peak gain is 2.4 dB. Radiation efficiency is 92% and system efficiency is 93%. The next frequency is 2.2 GHz. The radiation efficiency at 2.2 GHz is 94% and system efficiency is 90%. Let's look at 2.3 GHz next. The radiation efficiency is 94% and system efficiency is 93% at 2.3 GHz. The radiation pattern is directional and the peak gain is 2.3 dB. Finally, we will be checking the 2.69 GHz. The radiation efficiency is 93% and the system efficiency is 83% at 2.69 GHz. The peak gain is 3.07 and the radiation pattern is directional. With this, we know the antenna meets the radiation efficiency specification of 75% or higher across all the frequency of interest. This is the end of the tutorial. I hope you liked the tutorial. If you do, please click the like button and comment below. See you in my next video with another interesting problem. For inquiries, please email pragash@innovave.co or visit www.innovave.co.